Hello, in this video I'm going to take you through paper 2 of the 2019 Higher Chemistry paper. So, question 1a, you're given this reaction with sodium thiosulfate and you're asked initially to balance the equation. So, I tend to work through the elements from left to right. So the sodium's first of all, there's 2 on the left. So that means we need 2 on the right hand side. Then the sulfurs, there's 2 on the left and there's 1, 2 on the right hand side as well, so they are balanced. Then for the oxygens, there's 3 on the left hand side and 2, 1 is 3 on the right, so the oxygens are also balanced. Then for the hydrogens, there's 1 on the left and 2 on the right. So we need to put a 2 in front of the HCl to give us 2 hydrogens. And then lastly, the chlorines, there's now 2 chlorines on the left and there are also 2 chlorines on the right. So that's it balanced now. Next question. So the experiment is investigating the effect of concentration. And part A asks you to use a table to show the volumes of waters that would have been used to vary the concentration. So the important thing is if you're varying concentration by changing volume, total volume remains constant. So the total volume in experiment A and experiment E is 50, which means that if you add these 2 numbers together in each one, which means they all have to add up to 50. So to get 40 up to 50, you would have 10, 30, we need 20, and 20 we need 30. Okay, so 10, 20, 30. As long as the total volume is constant, that keeps the experiment fair. And then part B, calculate the time in seconds for the cross to disappear in experiment C. So this is experiment C here. We're given the relative rate. So the equation for relative rate you get in the data booklet on the contents page as 1 over T, but we are trying to find the time in this case. So we need to rearrange the equation. So you rearrange it to T equals 1 over rate. So because we're looking for the time in experiment C, we do 1 divided by the relative rate of experiment C, which if you put into your calculator, would give you 35.0877. Just watch your rounding for these calculations. So you could round it to 35.1 seconds, you could round it up to 35.09, you could round it up to 35.088. Just make sure you can round correctly, so don't round it to 35.08 for example, because that number is a 7, so that would be incorrect rounding. Then we move on. 1A, I will zoom in for this. Part 3. So here we're using the graph to determine the temperature rise required to double the reaction rate. So you need to pick 2 relative rates here, that one is double of the other. So you could pick 0.2 and 0.4, or you could pick 0.04 and 0.08. I'm going to pick 0.02 and 0.04. So then you look to see what the temperature was at those rates. So for 0.02, it was 44 degrees. And for 0.04, it was 56 degrees. So that's a temperature change of 12 degrees Celsius. So that would be the temperature rise you would need to double the rate. You should find it was 12 degrees whether you picked 0.04 and 0.08 to compare, or 0.06 and 0.12 should still always be 12 degrees. Then state 2 conditions necessary for the collisions to result in the formation of products. So for collision theory, the 2 requirements for a successful collision is that they collide with the correct geometry. So that means that, say, the functional groups would have to collide with each other And the second thing is that the particles have energy greater than or equal to the activation energy. It's important that you mention the activation energy. If you were to just say that the particles have enough energy, that wouldn't be sufficient to get the credit for this question. So you're best to just say that the particles have energy greater than or equal to the activation energy. So those are the two requirements for a successful collision. Then 1C part 1, we've got a potential energy diagram here for a reaction pathway, and it's asking us to draw an X on the diagram to show where the activated complex is formed. The activated complex is formed at the top of the activation energy peak, so you would just draw an X on the line there. Then part 2, copper 2 ions catalyze the reaction, add a dotted line to the diagram to show the change in potential energy with a catalyst. So remember, a catalyst lowers the activation energy of a reaction. So what happens is it doesn't change the energy of the reactants and the products. So the energy that the reactants have is here, the potential energy that the products have is this line here. And as the reaction proceeds with a catalyst, the activation energy is lowered, so the curve does not go up as high. But it needs to start and end at the same energy that the original and catalyzed reaction did. Okay. What you need to watch out for is that you don't overlap the line. So for example, you don't go up with that line and then just make it shorter. Okay, they need to be separate the whole way. So energy, potential energy of the reaction will be different for the entire reaction. It's only the starting and finishing energies that stay the same. Then question 2, given some blurb here about Dmitry Mendeleev. What a man. Love his periodic table. And you're asked to explain why the first ionization energy shows an increase going from lithium to neon. So lithium and neon are across a period from each other, so that's just due to an increase in nuclear charge. You can also say it's due to an increase in the number of protons in the nucleus as well. So if the nuclear charge is increasing because you've got more protons, that's going to more tightly hold the outer electrons that you'd be trying to remove if you were ionizing it. And then part 2, explain why the first ionization energy of potassium is less than the first ionization energy of lithium. So if you look at where lithium and potassium are in relation to each other in the periodic table, they are in the same group. So potassium is further down group than lithium. So down a group, it's always to do with the number of occupied shells, either causing shielding, more shielding, or the electrons are being less tightly held. So the electron arrangements of these elements are as follows. In the ionization, remember you're trying to remove an outer electron. So if you were trying to remove the one in potassium, there's a lot more electron shielding happening because of the more inner electron shells. So this outer electron here will be less tightly held compared to the outer electron in lithium, where there's not as much electron shielding because there's only this layer of electrons shielding the nuclear charge from the outer one compared to the 3 other layers of electrons in potassium. Okay, so for an answer, you would just want to say that there is a greater shielding effect in potassium, so the outer electron is less tightly held. So then 2B part 1, write the equation for the second ionization energy of nitrogen. So remember, there's the generic ionization energy equations on page 11 of the data booklet, where you're given the E plus G going to E2 plus G plus E minus. So this would be the generic second ionization energy equation, which is what we're looking for. But we want it for nitrogen, so all you have to do is replace E with an N, but everything else stays the same. You must show the gaseous state symbol, because one of the requirements for ionization is that the atoms are in, or the particles are in a gaseous state. And even though nitrogen exists as a diatomic element, that doesn't matter in the case of ionization. It's never shown as a diatomic element when it's to do with ionization. It's always just a single atom. Then part 2, explain fully the increase between the 5th and 6th ionization energies of nitrogen. So from this graph you can see that when you go from the 5th to the 6th, it takes a massive increase in ionization energy. So you're asked to explain why that is. So if you look at nitrogen, anything to do with ionization, the electron arrangements are useful to look at. So nitrogen's electron arrangement is 2, 5. Okay. If you have done the 5th ionization, then you've removed 5 electrons. So the product of the 5th ionization of nitrogen would have the electron arrangement of just 2. Okay. If you then want to go and do the 6th ionization, you 6 plus, and then you're left with just 1 electron. To go from here to here, what you're trying to do for the 6th ionization is remove an electron from a stable electron arrangement. And that always takes more energy. Okay, so it's hard, it takes more energy to remove an electron from a stable electron arrangement than it does from an unstable one, which is what it had up until this point here. The second point, because this is worth 2 marks, comes from you then also stating that the electron you're now trying to remove is less shielded because it's in an inner electron shell. So you originally were removing electrons from this second electron shell, which had been experiencing nuclear charge shielding from these electrons here. Okay, so because you're now trying to remove an electron from an inner shell, it's less shielded, so it's going to be more tightly held. Okay, so the electron you're now trying to remove is more tightly held. Okay, what you need to make sure you do is that you put in your answer what ionization you're referring to. So for example, you would have to say the 6th ionization is removing an electron from a stable electron arrangement, and it's removing an electron that's more tightly held as it's closer to the nucleus. Okay, so you need those 2 points for that one. Then C, ionic radius is the measure of the size of an ion, so we're talking about ions this time. Explain fully why the ionic radius of phosphorus is greater than the ionic radius of aluminium. So if we look at what these 2 things are as ions, so phosphorus would gain 3 electrons to get a stable arrangement, because remember that's why atoms form ions, is to get a stable electron arrangement. So it would become P3 negative. Aluminium would lose 3 electrons to get a stable arrangement, so that becomes Al3 plus. So the electron arrangements of the ions are 2, 8, 8, and 2, 8. So looking at this, you can see that the phosphorus ion has 1 extra occupied electron shell compared to the aluminium ion, which obviously is going to make its radius bigger because the outer electrons are further away. So for this question, for the 2 marks, you would need to specify what these 2 substances exist as ions. So just writing the formulas like I've done here would be sufficient, and then make a statement that phosphorus has 1 extra occupied energy level compared to the aluminium ion, therefore it's got a larger radius. Then question 2D. So you're given some information here with some equations. This is a problem solving question. And you're asked to decide or predict whether the structure of barium oxide is similar to cesium chloride or sodium chloride, and you need to include your calculated radius ratio in the question. So the ratio, right up here, so our positive ion in barium oxide is the A, 2 positive ion. If you turn to page 17 of the data booklet, you will find the ionic radius of that one, which is down near the bottom. So that's 135, so that goes on the top, so that's the positive one. And then the negative ion is the oxide ion, which has an ionic radius of 140. So if you put that into your calculator, you will get 0.96. Like it says down below, you need to include this calculation in your answer. If you then compare that to the two you've been given already, that means it's more similar to cesium chloride. So you need to also make a statement to that effect, stating that it's more similar to cesium chloride. So then question 3 is all about this melting point of non-metal elements. So that means you don't want to mention anything about metals, and it's asking about the structure and bonding and how it affects the melting point. So remember, for these questions, it's just marked on how good a knowledge of chemistry you demonstrate. So 3 is if you've got shown a good knowledge, 2 is if it's reasonable, 1 is if it's limited, and 0 is if you've shown that you have no knowledge. So things you could mention on this: for non-metals, you've got monoatomic noble gases. So you would want to fully explain, you could explain what monoatomic means. It exists single atoms, they don't form any covalent bonds, as they've got stable electron arrangements. In terms of the melting points of the noble gases, that's dependent on the LDF strength, because that's the only van der Waals force they have between the molecules. So when you are melting or boiling a noble gas, you are breaking London dispersion forces. Going down the group, the melting point increases, and that's because the strength of the London dispersion forces increase. And what you need to remember is that LDF strength is dependent on the number of electrons. So because you're increasing the number of electrons as you go down the group, then the strength of your London dispersion forces is also going to increase. Then you can move on to talking about the diatomic elements. So they are covalent molecules, and because they are diatomic, they will have more electrons per particle than the monoatomics. Therefore, they have stronger London dispersion forces, so their melting points are slightly higher. Then you've got the other covalent molecules, P4 and 4 looks a bit weird as well. Is that P4 and S8. So these two substances elements are covalent molecules, but they're slightly larger than the diatomic ones, because that would be like N2, where there's only 2 of them. For that reason, they have higher melting points again, because they're a bigger molecule, therefore they have more electrons, so therefore they're going to have stronger London dispersion forces that need to be broken when they melt. And lastly, you've got the covalent networks. So when you melt a covalent network, you need to break strong covalent bonds, which requires a lot of energy, which means that they have extremely high melting and boiling points. So the 3 covalent networks elements are carbon, silicon, and boron. And carbon is a covalent network in the form of diamond and graphite. Another thing you could mention in this answer is that carbon can exist as a covalent molecule as well, in the form of a fullerene. Okay, and so they have a slightly lower melting point, because in a fullerene, again, you're breaking London dispersion forces, but they are quite big molecules, so their London dispersion forces are fairly strong. You wouldn't need to mention all of these things in your answer, because there is no such thing as a perfect answer in these types of questions. However, you want to make sure that whatever you mention, you fully explain. So what I've written here you definitely not get 3 marks. It would maybe get you even 1, to be honest, because I've not actually written things out fully, but you would want to write in full sentences like you were kind of writing a mini essay. Feel free to draw pictures. You could draw a picture of essay and P4 if you wanted to illustrate your answers. You could talk about how London dispersion forces occur. So they occur due to a temporary uneven distribution of electrons around the nucleus, which creates a temporary dipole. So that's where the 2 sides of the atom are temporarily oppositely charged, and that can then induce a temporary dipole in a neighbouring atom, where they then have a temporary attraction between the dipoles that attracts them to each other, but it's very fleeting, which is why they're very weak. Anything other than that is not really to do with non-metal elements. You could mention the non-metal elements that they've got non-polar covalent bonds if they're a molecule, but you wouldn't want to mention ionic or any hydrogen bonding or permanent dipole, because that doesn't happen when you've got elements, because they don't have different electronegativities. Okay, so then question 4. State what is meant by the term enzyme. So an enzyme is a biological catalyst. You need to make sure you use the term biological, so that means it's a catalyst found in a living thing. Then part 2, we've got a bit of numerical problem solving. So we're to use this equation to calculate the percent mass of alcohol in the cider. So this tells you that a 50 centimetre cube sample of cider has this much alcohol, and 1 centimetre cubed of it weighed this. So we need the mass of alcohol, which we've got here, and the mass of cider. So we know that 1 centimetre cubed of cider weighs 1.36 grams, so we need to work out how much 50 centimetres cubed weighs first of all. So that means we need to do 50 times 1.36. So if you do that, 50 times 1.36, you would get 68 grams. So the mass of cider that they had in this sample was 68 grams. Then we need to plug it into this equation. So the percent mass is the mass of alcohol, which is 3.05, divided by the mass of the cider, which we've just worked out to 68, times by 100. So then if you plug that into your calculator, you will get 4.485. Again, just watch for rounding, so you could round that up to 4.49, or you could round it up to 4.5, as long as it's rounded correctly. So for example, if you were to have rounded it to 4.4 or 4.48, that would be incorrect rounding, so you would not get the mark. Then part B, name compound X from this reaction. So the easiest way to work out missing like products from reactions is to cancel out atoms that appear on both sides. So we've got this group here, it's the same. Then there's this CH that's the same. There's this OH that's the same. And then we've now got 1 carbon and 3 hydrogens left. So I'm going to do this carbon and 2 hydrogens, and then this 1 hydrogen that's left here. So then you can see what you're left with. So you're left with CO2, which is the beloved carbon dioxide. Okay, so that's the easiest way to work out what the products are, because atoms can't be created or destroyed, they can only change form. And question 4, part 2, is on some chromatography. So we've got some a TLC plate here, and different spots with different samples are detailed down below. And then the first question is asking to calculate the RF value of malic acid. So you're given the equation for the RF value here, the distance moved by the substance divided by the distance moved by the solvent. So if we go up, back up here, I'll just write the working on this page. So the RF value, the distance moved by the substance, we're looking for malic acid, is 4.1. And that needs to be divided by the distance moved by the solvent, which is 16.4. Get that here. So then if you put that into your calculator, you'll get 0.25. Okay, and there's no units for that. Then part B, the maturing process is complete when all of the malic acid has been converted to lactic acid and the cider is now ready to be bottled. Use the chromatogram to determine which cider is ready to be bottled. So we're looking for there to be a spot for malic acid, but no spot, oh sorry, no way around. We're looking for there to be no malic acid because it's all being converted, but we do want there to be lactic acid. So if we go back up to the chromatogram, so these are the control spots here, number 1 and 2. So we're looking for a spot at 8.2, but no spot at 4.1. So the only cider that has a spot number 1 and not spot number 2 is number 4, so that's cider B. So then 4C, the systematic name for glycerol, this is something you need to remember, it's propan or propane 1,2,3 triol. You need to get that in the marking scheme anyway if you weren't sure how to spell it. And then D part 1, explain fully why this molecule is water soluble. So thing to look for when you're looking for water solubility, so water is polar, which means anything that's also polar will dissolve in it because like dissolves like. So if something contains hydroxyl groups, that suggests it is polar, and the more hydroxyl groups it has, the more polar it is, because it can make lots of hydrogen bonds, which allows it to mix with the water that can also make hydrogen bonds. So for the answer to this question, you need to say that the molecule is polar due to having lots of hydroxyl groups, and therefore, because like dissolves like and water is also polar, it will be water soluble. But it's a good idea to look for hydroxyl groups if you're looking to see if a molecule is polar or not. Usually makes things easier. Okay, then 4D part 2. Name the carboxylic acid used to make this ester. So the ester link is here. If you split that in half, the carboxylic acid side is the one with the double bonded oxygen. So this would end up, if you were to break this ester up, back up into its reactant molecules, that would end up as the carboxyl group, and this would end up as the hydroxyl group when you add the water back in. Okay, so this carboxylic acid here, it's got 4 carbons in the longest chain, which makes it a butanoic acid. And then it's got a branch on carbon 2, so it's 2-methyl butanoic acid. So you can get that from the ester name if you remember to change the ending to anoic acid instead of anoate. The alcohol used to make this, although it's not in question, is this part here, so that's ethanol because that's got 2 carbons. Part 3, the molecule that terpenes are based on are isoprene units. You'll need to make sure you remember the name of isoprene as well, the systematic name, and be able to draw it. And then the functional group circled here is a carbonyl group, where the carbon is double bonded to an oxygen, and there's no OH attached to it. If there was an OH there, that would be a carboxyl group. And then part 2, further oxidation of ethanol can produce another product that spoils the flavour of cider, name this product. So if you oxidize ethanol, which is an aldehyde, you will make a carboxylic acid. The carboxylic acid that would occur from ethanol is ethanoic acid because it's got 2 carbons. So you have to specifically name the ethanoic acid because it tells you you're starting with ethanol. Then question 5, bond enthalpies. So using bond enthalpies and mean bond enthalpies from the data booklet, calculate the enthalpy change for this reaction. So you might find it easier to draw out the molecules to see the bonds that are being broken and made. Sometimes it's easy to forget there's double bonds in things. So you need to work out the energy required to break the bonds, and then the energy you get from making the bonds. So bond breaking is endothermic. That means you have to put energy in, and you can think of it as like karate chopping the bond. That requires energy. So we are breaking 4 carbon to hydrogen bonds in the methane. And then we are also breaking 2 double oxygen to oxygen bonds, because there's 2 moles of oxygen. So if you look up the bond enthalpy in the data booklet, which are on page 10, then you will find that the carbon-hydrogen bonds are each 412, so you times that by 4. And then for the double bonded oxygen, that would be 498 times 2. So if you put that into your calculator, you will get that, and then all you have to do is total that up, so add them together. So 996 plus 1672, and that gives you 2668. Okay. Then you do the same thing for the bonds that you're making. So we're making 2 carbon double oxygen bonds, and then there's 2 moles of water, which means we're making 4 oxygen to hydrogen bonds. Okay, if you look up those energies in the data booklet, the double bond of carbon oxygen is 743, and the oxygen to hydrogen is 463. So that's times by 4, times by 2. So then if you again calculate what that is altogether, that would give you 338. The bond breaking is endothermic, so that's a plus. Bond making is exothermic, so that's a negative. And then what you need to do is find the net energy difference. So you basically just add them together. So you would have 2668 plus negative 3338, which equates to 2668 take away negative 3338. So 2668 minus 3338 is negative 670 kilojoules per mole. Remember, the units are usually always given to you in the question, so you can always double check there to see what they are, and if you can't find them, it means you need to come up with them yourself. Okay, and then part 2, explain the difference between bond enthalpy and mean bond enthalpy. So this is quite a tricky one. If you have a bond enthalpy, that means that's a one fixed value for that bond, and which means it's because it's only in one chemical environment, so it will only ever be found attached to one other thing in one type of molecule. Okay, in the mean bond enthalpy, that bond could exist in lots of different chemical environments with lots of different other atoms surrounding it, which is why you have to take the average enthalpy for that bond. So bond enthalpy is where the bond exists in only one chemical environment in one type of molecule. Mean bond enthalpy is where the bond can exist in different chemical environments in different molecules. So then 5A part 3 is the molar volume. So there's a couple of ways you can do this. You can do it by direct proportion, or you can do it by calculating the number of moles. So I do it by calculating the number of moles. So I'll show you that first, then I'll show you also doing it by proportion. So we're asked to calculate the mass of carbon dioxide in grams. So I always write the thing I'm trying to calculate on the right hand side, and we're trying to calculate the mass, so I'll put in question mark. And that's produced by the combustion of 200 centimeters cubed of methane in excess oxygen. So because the oxygen's in excess, it doesn't determine how much carbon dioxide you're going to make, so you can ignore it. So the other thing we're interested in is the methane, so that's the CH4. And that's given a volume. We've also been given a molar volume here. So we are going to need to calculate the number of moles of methane. So we can then calculate the number of moles of carbon dioxide, which then allows us to calculate the mass. So because we're trying to work out mass, and we're going to use the NMGFM relationship for carbon dioxide. So the relationship for molar volume, you can use this triangle here. So N is the number of moles, V is the volume of the gas, but this has to be in litres, and that's because the molar volume is in litres per mole. So if we change this to litres, we just divide it by 1000, so that would give us 0.2 litres. So the number of moles of methane is 0.2 over 24. Sorry if you can hear my dog chewing a bone in the background. If anyone would like to come and take them away, feel free. So that ends up giving you 8.33333 times 10 to the minus 3. If you've not got a scientific calculator, it's probably come out as 0.008333. Okay, now that we've got the moles of methane, we want to use the stoichiometric ratio in the equation to work out how many moles of carbon dioxide we're going to make. So there's no number in front of them, which means it's a 1-to-1 ratio. There's 1 mole of each, which means we'll have the same number of moles of carbon dioxide. Okay. The gram formula mass of carbon dioxide is kindly given to us in the question. So now all we need to do is work out the mass by doing N times GFM. So if we do that, we will get 0.366666. So I'm going to round it to 0.37. Again, just remember to round correctly. Okay, so that's by doing a mole calculation. I'll show you now doing it by direct proportion. So with direct proportion, you always start with mole ratio. So we're interested in methane and the carbon dioxide. So 1 mole of this gives you 1 mole of this from the balanced equation. And now we need to convert the moles into masses and volumes. So 1 mole of methane has a volume of 24 litres. 1 mole of carbon dioxide, we're told, weighs 44 grams. Okay. We don't have 24 litres of methane, we only have 0.2 litres, so we need to find out how much 1 litre would give us first of all. So that would be 44 divided by 24. And then we multiply or scale up to find the volume that we actually have, which is 0.2. And then you would just type all that into your calculator, which would give you 0.366666 again, so 0.37 grams. So exact same answer, just done in a slightly different way. Then 5b, state the measurements required to calculate the mass of heptane burned in this experiment. So in these experiments, you need to weigh the heptane burner before the experiment and weigh the burner after. Okay, you have to specifically say you're weighing the burner because you can't weigh the heptane without the burner. So just make sure you don't make that mistake. Then part 2, calculate the enthalpy of combustion in kilojoules per mole for heptane using the experimental results given. So we need to use EH equals Cm delta T first. I'm just going to write my working on this screen because it's easier to see. So EH equals Cm delta T. And C is always in the data booklet, it's 4.18 kilojoules per mole per kilogram per degree Celsius. Because it's per kilogram, that means your mass of water, which is what M stands for, must be also in kilograms. So you need to divide that by 1,000. So 1 centimetre cubed of water weighs 1 gram. So that would be 400 grams of water, but you need it in kilograms. So you divide it by 1,000, and that gives you 0.4 kilograms. So that's the mass of water. It will give you the mass of heptane, but you don't need that in this pH. In this part of the equation, you use that later in the calculation, so don't let that confuse you. For EH equals Cm delta T, it's always the mass of the water that you need. So that would be 0.4. And then our temperature change, it's gone from 26 up to 49, so that's 23 degrees. You can plug that into your calculator. That would be 38.456 kilojoules. So now we need to use direct proportion to find out what the enthalpy of combustion is. Enthalpy of combustion is to do with the amount of energy you get when 1 mole of the substance is burned. So we know that we burned 1.1 grams, so 1.1 grams gave us that much energy. 4, 5, 6 kilojoules. Okay. We want to know how much we would get if we had 100 grams, because that's what 1 mole of heptane is. And it doesn't give you the gram formula mass of heptane, you just work it out from the molecular formula up here. So we find 1 gram first, so that would be 38.456 divided by 1.1, and then we'll multiply it up to find what 100 grams would give us, so 38.456 over 1.1 times 100. That is 3,000. So that would end up being 3,496 kilojoules, and it's a negative enthalpy change for combustion because it's an exothermic reaction, so the energy is given out. Okay, that would be kilojoules per mole as well, because the enthalpy of combustion is how much energy is released when 1 mole of the substance is burned. So then, question B, part 3. The theoretical value for enthalpy of combustion is slightly higher than the experimental value. It suggests why the experimental value is different. So there's always 2 reasons for this. You would only need to give one of them. So the first is that heat is lost to the surroundings. So in your experiment in the classroom or lab, you use a draft excluder, but they're not really all that great, so you still lose some heat to the surroundings. Not all of the heat is transferred to the water. And lastly, the other thing that can happen is that incomplete combustion takes place in your lab experiment. So that means that the fuel hasn't burned completely, which means you'll not get all the same amount of energy. Okay, so those are always the 2 reasons that your experimental values are usually not as good as the theoretical ones. It's because either heat's lost to the surroundings or incomplete combustion has occurred. Then question 6a. We've got these group of molecules called thiols, so this is like a problem solving question because you've not learned about these. State the reason why propan-1-ol was a suitable alcohol to compare with ethane thiol. So this was comparing the strength of intermolecular forces. So the difference between them is if you're using molecules to compare intermolecular force strength, they need to have the same strength of LDFs, and the strength of LDF comes down to the same number of electrons. So if you were to calculate the number of electrons in these molecules, you would find that they're the same or very close to being the same. So they're suitable to be compared just because they have the same number of electrons, so they have the same strength of London dispersion forces. If you're trying to determine the strength of other intermolecular forces and your London dispersion forces aren't the same strength, then it's not a fair comparison, because the strength of the London dispersion forces could affect it. Part B, explain why propan-1-ol is a higher boiling point than ethane thiol. You should include the names of the intermolecular forces broken when each liquid boils. So propan-1-ol has a hydroxyl group, which means that it's going to have hydrogen bonding between the molecules. That's the strongest van der Waals force that you can get, therefore its boiling point will be much higher. Ethanethiol, now depending on how you've been taught this, you might think that this is slightly polar, because the electronegativity of sulfur is 2.5 and hydrogen is 2.2, so there is maybe a slight dipole here. However, some people may have been taught that if it's a difference less than 0.3, 0.4, it doesn't make a difference. So in this case, you would actually get the mark either way. So you could either say that ethanethiol only has LDFs, which are weak, or you could say it has P permanent dipole to permanent dipole. I would encourage writing this out fully, but I'm just short for space. So but these two interactions, whichever one you say has, are weaker than hydrogen bonding, therefore the boiling point will be lower. Okay? But you would need to specify what bonds are in each one, like the question says, and then explain how then that affects the boiling point. So because hydrogen bonding is stronger than lunge dispersion forces or permanent dipole, propan 1 will have a higher boiling point. Then name the thiol that contains only one carbon atom. So this is ethanethiol, and it's got 2 carbons, so that suggests that the one with 1 carbon would be methanethiol. Then part 3 is another problem solving question. So a little numerical one, nobody really ever likes these. So for these, you want to set out a relationship in like an equation form from the question. So the minimum concentration of ethanethiol in air is 2.7 times 10 to the minus 7 milligrams, and that's in 1 centimetre cubed of air. Then it's asking to calculate the mass, that's the mass side, of ethanethiol that needs to be present in a room containing this many litres of air in order for it to be detected. So we're trying to find out how much we would need if we had this many litres. Because this is in centimetres cubed, we want to change this to centimetres cubed as well, so we just want to times it by 1,000. Just add 3 zeros onto the end of this. Okay, so we're wanting to try and find this, so I'm going to flip the arrow around. So to go from 1 to 4,000, whatever number that is, it's very big, we would multiply, so you would just do 2.7 times 10 to the minus 7 times 43900. And then if you put that into your calculator, 2.7 times 10 to the minus 7 times 49. So that gives you 11.853 milligrams. So that's how much you would need for it to be detected. Then for part 2, B part 1, suggest why 2-methyl-2-propane-thiol is classified as a tertiary thiol. So this is similar to why something's a tertiary alcohol. The functional group, if the functional group is attached to a carbon that's attached to 3 other carbons, that makes it tertiary. Okay, so this is a tertiary thiol because the thiol functional group is attached to a carbon that's attached to 3 other carbons. Then part 2, part 2a, draw the structure for the other isomer formed in this addition reaction. So if you look at the one up here, they've put the thiol group on this carbon. Yeah. So all you would do is switch it round. So instead of having it here, that would be the hydrogen and that would be the thiol. So you're basically just drawing this molecule with the groups every round. Okay, then part B, calculate the mass in grams of. So chemist obtained 84% yield. Calculate the mass made by the chemist. So this is a percentage yield. question, so that always has to start off with calculating the theoretical yield. So that for working out theoretical yield, you use the balanced equation. So again, you can do this by working out number of moles or by doing it by direct proportion, but I'm just going to do the numbers of moles. So we've got the 2-methyl propane, we're starting off with 30.5 grams. The gram formula mass of it is 56 grams. So that means the number of moles we had was 30.5 over 56. So if you put that into your calculator, you might be able to hear my dog snoring now. Okay. So that's 0.54 moles if you round it. Okay. Then we look at the ratio, so it's a 1-to-1 ratio, which means we would make 0.54 moles of the product, which if we then convert that into a mass, which we need for this percentage yield equation, we would have the number of moles times the gram formula mass. So that would be 0.54 times 90.1. That's the gram formula mass of the product. So that would be, then we would get 49.1 grams. Your number might be slightly different depending on what you typed into your calculator. So that's the theoretical yield. So then we use the percentage yield equation. So you've got the actual over the theoretical times by 100. Okay, so you can either do this by plugging the numbers in and rearranging. So you've got the percentage yield and you're trying to find the actual yield, and you've got the theoretical yield. So you have to rearrange that so that you end up with the actual yield as the subject of the equation. However, we know the yield's 84%, so you're really just wanting to find 84% of 49.1. Okay, so depends how you lay it out. You maybe lay it out as 84 over 100 times by 49.1, or maybe you do 49.1 times 0.84. Either way, it's going to be the exact same thing. So that then gives you an actual yield of 41.22 grams. Yeah. And we're going to stop this video there.